Hi, my name is Joe DeRossi, and welcome to the third and final video of the series. Today we will be talking about phases of matter, or more specifically, the different states of matter and what happens when they change states. In this video, we will specifically be talking about solids, liquids, and gases, even though there are more than just three. There's plasmas, BECs, but we won't get into that in this video. Alright, just a kind of summary of the different states of matter we'll be talking about. The first one we have is a solid. And a solid, this is a solid for water. And a solid holds its shape and has a fixed volume. And this is because the molecules in water are all bonded together. And it's not completely still because all the molecules are vibrating. But they're bonded together so they can't move, per se. And the second state we have is a liquid. A liquid molds to the shape of its container, has a free surface, and has a fixed volume. And in a liquid, the molecules kind of slide around each other. So they're not held together, but they slide around. Like they slide around against each other. And then the third state we have is a gas. I don't have a good example of that right now, but if I were to boil water, the water becomes hot enough where it has a phase change and it goes from water to steam. And with the steam is a gas. What happens with the gas is that the particles don't slide around. They go in all the different directions, but sometimes they'll hit against each other and bounce off against each other. Important thing to note is how the particles or molecules in a substance interact at different temperatures. At a higher temperature, the particles will be more excited, so they move around faster. So, for example, if there's like a container and you put it in the freezer, it's going to shrink. And I have a perfect example of that. Over the weekend, someone left some really shitty alcohol, pardon my French, at my house, and I threw it in the freezer. And as you can see, before I put it in, it was all the way, it wasn't contracted like it is now. And you can see it's shrinking a little bit. That's because the air inside the container is slowed down a little bit so that it shrinks. And you can see examples of that if you put a balloon in the freezer or you put a balloon in ice. There's plenty of different experiments for that. Another interesting side note is how phase change affects water. Now, water is densest at 4 degrees Celsius, and any temperature lower than that, it starts to expand and becomes less dense. And this is very essential because if this didn't happen, ice would be more dense than water, and we wouldn't have the top layer wouldn't freeze. So then I don't know what I'm saying, so I'm just gonna stop. Another interesting side note, or at least something I thought was very interesting, is that water is at its most dense state at 4 degrees Celsius. And this is important because at any lower temperature, ice starts to actually expand rather than condense like most other materials. This is important because without that happening, the ice at the top would just sink to the bottom and everything would just become frozen. But only the top layer becomes frozen, and that allows water, or not water, the organisms beneath that surface to live. Whenever we deal with phase changes, we have to do an additional formula for the amount of heat given off, which we get here. Q, or the amount of heat given off, is equal to the latent heat times the change in mass. So from change in mass is just ice going from ice to a liquid, or liquid going from liquid to a gas, and the amount that changes. two other important formulas to note are Q equals mc times the change in temperature, or the energy transferred is equal to the mass times the specific heat. Specific heat is the substance of a substance is the heat capacity per unit mass, and times that by the change in temperature. And then the other important equation is Q cold is equal to negative Q hot. Alright, for my problem, I will be doing number 19 from chapter 20. I don't know if you can read it. It states that a 75 gram ice cube at 0 degrees Celsius is placed at 825 grams of water at 25 degrees Celsius. What is the final temperature of the mixture? So first, we set up the problem by writing Q cold is equal to negative Q hot. That is our equilibrium equation, since they will both be the same temperature. And then I write out the formula. Which we get with this, and then we plug all the numbers and all what we know for what specific heat for water and ice is. So we get 0.075 kilograms times let me find it here. .33 times 10 to the 5 plus 4186 T final is equal to 0.25. 4186 T final minus 25 Celsius. This is what we get when we write out the whole formula with all the numbers, and then we solve for T final. Alright, to kind of shorten the length of the video, I did the calculations. So here you see I separate T final is equal to 61,361.25, should be joules, and divide it by 3,767.4, and that gives you 16.3 degrees Celsius. That is it for my video. I hope you enjoyed it as much as I did.